Hello, Physics Nation. My name is Nate Larmond, and I'd like to derive Kepler's third law of motion. So, it relates the orbital period to the orbital radius. Sounds complicated, but it's actually really easy. It's just four mathematical models. And the first one is Newton's second law. So, sigma F equals ma. So, what's the phenomenon? Well, it's an orbiting satellite or an orbiting planet. We're just going to put the sun in the middle, and then Earth orbiting around the sun, or you could think of M2 as the Earth in the middle, and M1 is the moon orbiting. Anyway, it doesn't really matter. Let's pretend this is a circular orbit, so we're going to say the centripetal acceleration is v squared divided by r, and that's our first substitution. So where a is and F equals ma, we're going to substitute in v squared divided by r. So this is just the circular version of F equals ma. Centripetal force equals mv squared divided by r. Except this velocity is a tangential velocity. So we can say the circumference of the circle, distance, divided by time, the period, the orbital time to get through one cycle, is the tangential velocity. So that's our second substitution. Where v is over here, we're going to put in 2 pi r divided by period. And I've already distributed the exponent. You can see 2 pi r divided by period becomes 4 pi squared r squared divided by the period squared, t squared. Except this is all divided by the radius. So I like to just multiply by t squared divided by t squared. This is 1, so this is a legal operation. And then on the top of the fraction, the numerator, it cancels out. That's how I like to think of this t squared term coming down to the denominator. Anyway, we can algebraically clean this up a little bit. We have an r squared on top and an r on the bottom, so one of those r's cancels out in the numerator, and we are left with a single r. So that is the centripetal force in terms of the mass that is orbiting, and the orbital radius, how far the mass is, and the time it takes to get through one cycle, the period. Except what's pulling this satellite through? What's preventing it from moving in a straight line? Well, gravity is. So that's the last substitution. That's the fourth mathematical model. The centripetal force is the force due to gravity. So we just set these two expressions equal to each other. And then again, we simplify a little bit. Let's see, if you multiply both sides by r squared, cancels out on the left-hand side and you get r cubed. And what else do we do? We're going to divide both sides by the universal gravitational constant, capital G right here. And then we're going to multiply both sides by t squared. So we're getting close to isolating orbital period. We could take the square root of both sides, and that would be period as a function of orbital radius. So this is Kepler's third law. He said the square of the orbital period was proportional to the cube of the orbital radius with this constant in front of the function. So thanks for watching. See you in the next video.